So I put Felix in an unfair spot here. See, I learned from Richard Hazeltine years ago that if you ask people way in advance, they always think they'll have time to do what you ask. And so when I asked Felix to give a talk on this, he thought, oh yeah, he'd have time to figure out how to do things in the pedestal. But of course, it's a really hard problem. So this talk is designed to provoke discussion, I think. I think there'll be a lot of discussion. It's clear we really don't know what's going on in the pedestal as far as turbulence is concerned. And Felix is going to try to give some of his thoughts on it, and interrupt, ask questions.
Sounds good, yeah.
I think we have plenty of time.
We have half an hour,
and
right?
Frank then will give a talk after this on some gene results. He's not here yet, so he's probably getting gene results for us then. Okay?
Okay, so what Peter was saying actually, is intended to be just a preliminary discussion on possibility of doing gyrokinetics in the pedestal, and the idea is doing the calculation based on the ordering that Peter and Grisha did, in which the pedestal is of order of the poloidal armor radius. In this talk is going to be just electrostatic formulation, but obviously need the extension to electromagnetic case because we know that there is electromagnetic turbulence out there. Okay, so what are the orderings? Here I'm assuming that we need to suppress the turbulence with the pedestal. That's what all we believe is doing. So we need the parameter gamma e, which is just the space derivative of the E cross B velocity, has to be of order the growth rate. That's a measurement of the time scale that we need to have here. And I have written the growth rate as some non-dimensional parameter, the ion thermal speed divided by the scale length of the temperature. I mean, this is a very strong scaling. Doesn't need to be like this. It's possible that there is a exponent here, which is less than 1, that will help us do orderings. But I mean, I think this is the strongest case. So if you use this equation to estimate the size of the potential, you basically get this. You get that there is the non-dimensional parameter in front, which could be small. In some cases, it is small. And you have that it scales with the scale length of the potential to the square divided the ion gyro radius and the scale length of the temperature. That's what your potential has to scale like if you do this kind of estimate. So there are two possibilities. One of them is what I think almost anyone that has done any pedestal is going for, and that is you have high flow, in which you order the potential scale length as the temperature scale length and make that much bigger than the ion gyro radius. Then you get that according to this scaling, you get that the size of the potential itself has to be much bigger than the thermal energy in the plasma. The problem with this ordering is that because you are making the potential much bigger than the temperature, you cannot make the pressure and the potential gradients compete. And then you necessarily immediately get to sonic flows, which are actually not observed in pedestals. Even in cases where we have neutral beams, the near sonic flows are in the middle, not at the edge. So the edge doesn't have strong flows. It must be that the ordering should be ordered, right? So here is what I'm proposing then is getting some kind of low flow that does contain the physics of the pedestal. And to do that, what I'll do is that first of all, if you get this dependence of with gamma, the growth rate, you don't want the growth rate to become comparable to the gyro frequency. So if you don't want that to happen, you need that the biggest scale length here is actually a temperature scale length. If that becomes of the order of the gyro radius, you are actually screwed, and you get a growth rate that is of the order of gyro frequency. So we don't want that. We want the length to be bigger. Then if we make the order of the potential comparable to 1, to electron temperature, to be able to make the pressure gradient and the potential gradient compete with each other and have flows that are not sonic, this expression gives us that the potential and the density scale lengths, that's where it goes into the ordering, Peter's ordering, have to be between the ion gyro radius and the temperature scale length. If you have an ordering such as this, what you are getting then is that you have gyrokinetics is possible. You have typical time scales that are below the gyro frequency. You have possible competition between the potential, the pressure gradient and the potential gradient, and actually you get suppression of turbulence according to this simplified point of view. So this is actually the approach that I'm going to take. This one here. Any questions so far? Yeah.
In estimating the growth rate with LT, you assume that it's driven by the temperature gradient.
Yeah.
But if you order LT much larger than Ln, don't you go into the regime where possibly it's the density gradient will drop?
Yeah, but those are trap electron modes. Yes, it's actually possible, but I'm thinking that I'm hoping that the pedestal, when it actually goes into the pedestal, the trap electron modes are not excited or not very much.
So let me simplify the question. If it's driven by a density gradient, don't you get into the same problem with the ordering?
Yes, so that's why I think that it shouldn't. I mean, the temperature gradient is going to be the ion, okay? And there's going to be an electron scale length in this whole thing. So if I want to make this work, I need actually to avoid trap electron modes. And this is actually what I'm considering here.
If you leave the measurements as exactly, for example, then eta E is in the range of 1.5 to 2.5, eta I is for a unity.
Mm-hmm.
So there's kind of a fundamental difference between.
Well, yeah. Okay. So here we get into the problem of how much we can believe in this, right? And actually, what are the pedestal we're comparing are those lengths actually of the order of rho poloidal, right? I mean this. Okay, so
At least whatever they are comparable to each other.
The eta I and the eta E.
I don't.
Are roughly speaking therefore the unity. So Ln, LTI, LTE
Yeah.
are all similar within a factor of 2 or so.
But presumably the temperature scale length is measured from the purity.
Well, they recently spiced up their measurement technology, and they believe that they have good ion temperature measurements now in the edge. Of course, you can always improve, but in any case, those numbers haven't changed much over many years. I mean, you can argue about a factor of 2, but not a factor of 10.
So if that's the case, probably gyrokinetics doesn't work, which could be the case, right? I don't want to get in. So if you actually get to a point where you have that, I mean, you want an ordering in which you have low flow ordering, in which the potential size is actually of the order of the thermal speed, the thermal energy, and I mean things come out quite well out of this. That would mean then that possible this we can't apply it there, or yeah, I don't know. I mean, I don't want to. This is I prepared this trying to recover what Peter has already done. That was the idea, trying to get into that limit some other way. I don't know. I'll have to. I guess.
I think you could try to distinguish between L phi and Ln and the others.
Then you get high flow. Then you get sonic flows if you do that. Yeah. So that's the hard. Well, yeah. I mean, I do agree that some measurement seems to indicate some others. Mass, for example, as I was saying before, it has 0 gradient in temperature. So I don't know. I myself don't know exactly what to believe there. So if we want to reproduce Grice's and Peter's ordering, what basically you have to do is order the temperature scale length as the B or B poloidal square, when we assume that B or B poloidal is actually a large parameter. Then that means that the scale of the potential and of the temperature is actually, oh sorry, I put temperature is actually density here. It's actually the rho poloidal. Basically, it's the scale length of the potential and the density is actually the poloidal armor radius, and that is actually bigger than the ion gyro radius.
When you say LT, you just mean the ion temperature?
The ion temperature, exactly, not the electron.
You don't care what the electron is.
I'm going to talk about the electron temperature at the end, but for this argument, it's only the ion. So now I'm going to try to justify in what Peter. I'm going to repeat Peter's argument on the temperature gradient. And this is very important because that actually kind of closes the argument and tells you you have actually to assume that the temperature gradient is actually small. So that, I mean, and the argument is just basically an entropy conservation, right? You have the production of entropy, which I'm going to assume now. Imagine that I have a non-Maxwellian distribution function. It goes like this. It's actually the collision frequency, my density that I have in there, and actually the volume in my pedestal, which is actually the surface of the flux surface and the poloidal armor radius. And if I prove that that production is much bigger than the entropy I'm taking out of the system by just transporting it, which is this is a very simple argument, just basically saying I have some heat flux in my system which is crossing it, and in both sides of my pedestal I'm going to assume I have a temperature increase. So this is another magnitude expression based on typical thermodynamics of what you get if you assume that that's the case as what the entropy that you are taking out of the system. And if I assume that this Q is actually coming from within the tokamak and is gyrobomb, I get this kind of estimate for the how much entropy I can pull out. So I have to impose that this is much bigger than that. And if I impose that, what I get is that my collisionality parameter has to be much bigger than the rho I over A, which is the minor radius of the tokamak. And I'm actually having this parameter, the one inside the tokamak, because it's coming from the gyrobomb in the core. So as long as you have this satisfied, you have that you produce entropy much faster than you transport it. So eventually you'll get to a Maxwellian. If you get to a Maxwellian, you must have constant temperature in a pedestal that is of the order of rho poloidal. And this actually, I mean, is somewhat satisfied. I think it's pretty well satisfied in reality. It's like an order of 10 to 100 in pedestal, I think. If someone thinks different, correct me. So actually it seems to close on itself. It seems that at least within the separatrix and possibly even out there, we have a Maxwellian, and the temperature has to be a constant. So everything closes. So by assuming so, then I'm going to try to come up with a delta F simulation, a way of doing delta F simulations in the pedestal. And to do that, I'm going to split the potential, the surface potential, into background and turbulent. The background one is the one that is comparable to the thermal energy. It has a scale length of the order of rho poloidal, and then I have a turbulent potential, which is a small, and here I use just a mixing length argument to estimate the size, and it's small in B over B poloidal over B to the square. And it has a scale length of order the ion gyro radius. If I use this scale length, then I can use the old gyrokinetic variables. Yes, Per?
How big are the potential fluctuations experimentally?
No.
So one can presumably.
Probably you can measure them, yeah. So it depends, I guess, right? I mean, if you have an elm is order 1. But between elms, I don't think it's that large. I don't know exactly the size. Does anyone? So I can use the gyrokinetic variables, the typical gyrokinetic variables, the gyro center position, the total energy, the magnetic moment, and by using those I can actually write a delta F equation, which I'm going to explain term by term right now what the new stuff comes in. Actually, there's only one place where it becomes different from, two places actually, where it becomes different from the usual gyrokinetic equation. Well, you know, this is the time derivative. This is the E cross B, the background E cross B, which gives you the background E cross B CR, and it's going to CR your turbulence. You get the parallel component, which before usually we write as B parallel B dot grad theta, but now because we have Peters ordering, we have to include the E cross B piece into it. And that E cross B is actually going to modify your banana orbits and drift orbits and give you the new results that Peter found. Then we have the magnetic drifts again, which now you have to wonder if they are or not important. And this is the parameter to find out if they are or not. So they could be small. It could be that magnetic drifts are not so important according to this ordering, but I'm going to leave them there. Then the nonlinear term here, the typical nonlinear term, the collision operator, right? This is it comes from energy conservation. The time derivative of the potential comes in, and then we have the typical drive terms in gyrokinetics. But now we have to be careful. Now we were ordering differently the density gradient from the temperature gradient. So in principle, this here should be bigger than this term by a B or B poloidal. That's what if you remember, let me go back and this kind of ordering tells you that the term that I was pointing out, this one, should be bigger. However, because we are in low flow, these two terms cancel to first order, and then they become small, and now become comparable to this other term. Okay? So now we have an equation that is almost all the terms are the same order. And let me get to the next slide to actually compare this one with the electron equation with this one, and you'll see where the difficulty lies. If we, yes, Per?
So the only new term compared with the usual gyrokinetic equation is the last one on the top.
Yes, that one. But
the second term normally kept?
Yeah, the second term is normally kept, but that's what I'm gonna talk about right now. That's where the difficulty lies, really, in this formalism. For the electrons, I can just use the typical approximations and get the equations for the electrons, which you can see are actually equivalent to the ions, but we don't have that term in here. And now you're gonna see how I have written different sum terms in particular. So here we have the time derivative and the streaming due to the A cross B. This becomes a shift plus the shear of the A cross B. A Doppler shift plus the shear in the A cross B, right? That's what this term does. If you come down here, you see that this term, you see this term here that I combine with this to make it small. Now, I've written to make this again a time derivative and the A cross B transport of the potential. And that's important because then the potential and the electron distribution function, both of them have the same Doppler shift. But in the previous case, because I had to combine them into one term to make them of order 1 over LT instead of bigger, that term doesn't actually combine, and the Doppler shift that you get for the ion distribution function, you don't get for the potential. And that's actually the problem we're going to run into. For the quasi neutrality, I just put it for completeness. It's exactly the same that we are used to. And here is the problems that we can find when we try to solve these equations. I'm almost done now. The problem when we don't have that Doppler shift in the ion equation is that we cannot use the typical technique that we use in flux tube simulations, in which we use a radial K that varied in time, because we had everything Doppler shifted and it was moving, and that increased that decreased our radial wavelengths. That we cannot do anymore, so we need global delta F to actually solve these equations and get anything out of them. And now this is just a discussion on how I think we can actually feedback into the profiles of potential, density, and temperature. And what I propose is what is being done in a group for a while. Is actually using flux surface average, conservation of particles, momentum, and energy. And then we could use this actually to close the system. If the electron, particle, and energy transport is actually very, very simple, because the scales of the electrons are actually below rho poloidal, the poloidal armor radius of the ions. So we could actually calculate the density and electron temperature profile within the pedestal by using this scale difference. If we use the ion energy transport and ion momentum transport, we could find actually the temperature, the ion temperature, and the potential, the zero for the potential. And that's because when we solve the ion momentum, we get the rotation, and from the rotation we get the relation between the potential and the pressure, the ion pressure gradient. Because this is actually something that I need to think more about, but my opinion at this point is that if we are going to solve the equations under assumptions that Peter had, but that basically that we have a Maxwellian that extends over the whole volume of the pedestal, we need to solve these transport equations over the total volume. We integrate over the volume, and we get the total energy inside and the fluxes that come from the sides. And that will tell us what the ion temperature is and the potential is in there. And I wanted to add too that because we are in the low flow ordering, the equation I showed before doesn't even contain enough information to solve for the momentum transport. And we need to carry it to another order in B or epoloidal, which can be done. This is an order higher in B or epoloidal of the equation I showed before. But I haven't done, I mean, I didn't have time to do here. So it is possible, like this is just the final end, so we can discuss. It is possible to obtain a delta F formulation. It has the trouble that the potential and the ion distribution function don't have the same Doppler shift. So I don't know actually how to attack that numerically. In this whole argument, the entropy argument was crucial. So, I mean, if that fails, then we need to go to full F, and we cannot do this kind of derivation. It is possible to obtain the transport equations I was saying, and when I mean global, it's actually integrated over the whole volume for the ion temperature and the potential. And a question I raised at the end is that I have used the bipolar expansion parameter the whole time, but I don't think it's probably a fundamental parameter. I mean, you have H modes in spherical tokamaks, so this needs to be extended somehow in cases where the toroidal and the polymagnetic field are comparable. And I mean, that's all I can say at this point.